Hello everyone, my name is Elvira Rakova from Direktin, and today I would like to share with you one use case of the steel manufacturer with whom we optimized their compressed air system. As you know, everyone says to measure is to know, but sometimes the answer it's not evident and we cannot even relying on the measurements. We still need to understand what is the problem and what are the ways to optimize. This is why Direktin we're using our own software that we developed, Direktin easycas, that helps us to see what can cause the problem, how the problem can be solved, and as well as to show the energy cost and the optimization cost after the project. So let's start. Today, we have a manufacturer. This is a Maghreb Steel manufacturer. The factory produced the metal sheets using the cold rolling machines. And for this cold rolling, they are using compressed air mostly for the cleaning process. After installing efficient components and replacing the open pipes that they had before by engineered nozzles, uh, everything seemed to be good. However, the customer started to encounter the problems in the downstream operation. So basically, the pressure was not enough. It was a lot of pressure fluctuation. It also uh, impact a lot the quality of the product. The maintenance manager, they saw the pressure drops in the downstream, and they asked for the detection for the measurement. The measurement confirmed that there was a pressure fluctuation around 3 bar, pressure drop in the downstream about 1.6 bar, as well as there was some energy consumption data. And this was basically also based on the fact that there were 13% of leaks. However, even having this measurement data, there was not conclusion of how to solve the problem. And this is where we started our project. So basically, we started with an on-site audit of the application because we always start with the application, and this is our specialization. And then we put all the data that we got and gathered from the on-site audit as well as from the previous audit of the energy performance of the system into our Direktin easycas model. So a lot of companies usually start with the analysis of the compressor room, but we usually start with the analysis of the application. And the first type, I would like to show you the modeling of the application of the air knives that were installed inside the machine into the production. And to start, I would like first with the model of the application. So first of all, a very important thing that we took the air knife that was provided by the supplier, and the customer thought that it might cause the pressure drops, and we did the modeling of this. Opening the software, you can easily download from the website. I want to show you the model of the nozzles. So basically on the right hand side, we have here the nozzles that are used for this air knife. Simply by connecting them and using the tubes and that was suggested by the manufacturer, we drag and drop it here, and we modeled the nozzles connected in the air knife as well as the open tubes that supposedly were replaced before with the diameter of 7 millimeters internal diameter as well as the pressure level of 4 bar. So let's see what we actually get. So after pressing on the calculate and not forgetting by the entering the input parameters here, let me get the input parameters, you can see that the open tubes, they consume about 1,200 cubic meter per hour. That will result in 68,000 Moroccan dirham it was in this case. And the problem is here that if we use the same the same connections, it results in a very high pressure drop. So here you can see the delta P, the very high pressure drop. So this shows us obviously that we also need to have a very high level at the compressor. And this might not be the case that it was exactly replaced by all these open tubes. Probably they were less at the beginning, so it helps us to understand the initial situation. However, when we need the 4 bar out here in these nozzles, this is how it was projected, we should have here about 10,000 Moroccan dirham of the energy cost based on the 600 cubic meter per hour, and the required pressure level here has to be 6.2 bar. So basically it just shows us that the connections here were not planned correctly by the machine manufacturer, because what customer did, he replaced only one part of the machine without changing other connectors that what they were installed before. And this would have resulted in a very high pressure drop, around 2.2 bars, as you can see there. If we model here for the 5 bar, as it was also planned and projected for the machine, the pressure drop will be around 3 bars. So this gives us already an understanding that the machine doesn't work and doesn't provide with the pressure level of 4 bar or 5 bar here, because we saw in the manometer, and we also have a measurement, that the pressure here was not was the operating pressure here was about 3.5 bar, so it was way lower. So what I wanted to say here, that this model shows us that the system was not working as projected. Because if it have worked as projected, we needed to have the 6.2 bar for the operation here. And in the reality, we had 4 bar for the operation, even lower than 4 bar for the operation here. And this gives us also an understanding that the real operation was lower and was about 2 bar. So let me show how it will look like. So we take here the nozzle of 2 bar and we connect it. So we need just to do a couple of, well, there are 12 of them. We connect. So once again, the machine operation here showed that the pressure level before the machine was 4 bar. So with all this design that was on the machine, it shows us that the pressure level wouldn't be able to reach 4 bar in the output. So, and this explains why there were complaints also from the operators that the level of pressure was not enough to operate this machine. So this we also can prove by modeling the application that we suppose is real. So the real application, we suppose it's with a lower pressure level, so around 2 or 3 bars here. So we model it and then we insert this application in the machine, and we can compare it with the manometer that shows us during the operation, and also with the compare it with the real measurement data. So this is basically the real situation, that the pressure at the inlet of the machine was fluctuating, and around 3 bars was in the entering of the machine, or 2 bar. Then here on the outlet, we had around 2 bar, and this would correspond to the blowing force, not of 10 Newton, but let's recalculate the blowing force, because we can compare it with the open pipe, of 6.3 Newtons. So And the projected application was for 120 newtons. However, the applications that really was used, it was around 70 Newton of the blowing force. And this was questionable for the operators. So sometimes they said it was fine, sometimes it was said it was not good. But the main concern here is the high pressure drops in the downstream, pressure fluctuations inside the machine, as well as the pressure drop in the compressed air line. As the next step, we go now to model the compressed air line. So let's sum up the results of the first phase of the modeling of the application. We had an input data as a technical documentation, including the design and operation conditions. We created the model of projected application where the consumption was for the 5 bar around 741 cubic meter per hour with a required pressure of almost 8 bars and blowing force about 120 newtons. So this showed us that we had the high pressure drop around 2.3 bar only in one connector. So the results, we can compare the model with the technical data. 740 vs against the 720. The blowing force that we calculated and modeled was about 127 and promised in the data catalog 120. So the correlation are very close. Is very close. The connection of the application showed that the possible pressure drop was 2.3 bar and that we required the pressure at the application of 7.9 bar. That was not actually the case at all in the facility. However, the modeling of the real conditions showed us following results. The connection of the application still has a pressure drop about 0.8 bars, and the required pressure at the inlet of the application is around 3 bar. So was correlating with the measurement data. So when the machine started to work, the manometer would drop until the 3 bars. The outlet of the application is about 2.2 bars, so it's quite low pressure that results in the blowing force of 70 newtons, and the consumption there was around 366 cubic meter per hour. With this data, we now that can model the full application and compare it with the data with the audit. Let me now show how we did it in the model itself. So as the next step, what we did, we took the air knife that we projected in detail, modeled in the software, and we put it as the generalized consumer. So there are two machines with 4 air knives each, and we just pressed on calculate to model it. And as the result, we got 6.4 million Moroccan dirham, so 6.5 of the energy cost per year. That correlates with the real energy cost. But the most important thing what we also got is the information about the pressure drop in the pipelines. The thing is that there were some problems in the machine, not the problems, but the modifications and updates that should have been done while changing and updating all other components, but as well as the full compressed air system should have been adapted to the new components. We always need to remember when installing a one efficient component, we need to check the compatibility with the existing system, because efficient components doesn't necessarily means that it will consume less, but it might require different pressure level. It might require also different mass flow rate that is different from the volumetric flow rate, depends on the pressure level, and this might cause also higher pressure drop. So in this case, we got a real picture that the pressure drop were around 1.8 bar, and there were also some minor pressure drops here. While using the model, you can go into the optimization and choose here the allowable pressure drop that the program will show you. For example, I ask now the program, don't show me all pressure drops below 0.3 bar. So I press on calculate, and now I have only 2 pipes here. So this is my limiting component, and I can see right away how my system will change if I replace this pipe diameter by another one. So I just click on replace by changing, click on replace also here, and to see what's gonna happen. So I just choose it from the catalog. Here you see it's already 4.7 from 6.5 by replacing the system. However, we need to remember that the air knives there were not suitable for this machine, or machine is not suitable for this air knives. And we need to revert and once again calculate how the compressed air system should look like to be able to operate the air knives that were projected for this application, meaning that we will have the 120 Newton of the blowing force with the output pressure of 5 bar. Let me now show the next step, the results, how the system should look like. So the next step. Let's imagine that we changed something inside the machine. So we changed those connectors, and now we're integrating our projected system into the compressed air system, into the existing one. So we want to have 120 Newton of the blowing force, the pressure 5 bar. So we're going to have some pressure fluctuation after we change the air knife. So this was also another additional step of not changing the air knife, but changing the connector there. And then we would model it, and the model showed us that the required pressure in the compressor would be 12 bar, as well as required flow rate will be twice as much, resulting into 24 million Moroccan dirhams instead of 6.5. What it shows here, of course, it didn't work that way, and we saw the reason why. But the compressed air system is not designed to operate with this new equipment. And this is always need to remember. It's always good to integrate new efficient applications, and replacing open pipes by the efficient nozzles or cylinders by more efficient cylinders. But we need to always understand that the system has to be adapted to this, because the energy costs, they come from the pressure level at the compressor. They come from the resulting pressure drop, as well as volumes that we need to fill in this system. So therefore, before installing something new, or even installing any efficient solutions, by having just a technical data, is important to create a small model. So you can use Direktin software that is free to use. Just put all the components that are in the system without maybe certain details. As you see, this model is quite generalized. So because in terms of the components, we had the consumers, we have the simplified compressor, as well as in this software, you can calculate the air tanks, retention time of air tanks, choose the size of air tanks. So there are no certain specific elbow connectors or any other things, but you can add more detailed components from the catalog if it is available, if you have it also available from the layout of the system. However, it's enough to spend just 2-3 hours on the analyzing the existing system by using simple model. So, and at the end, we had 4 options that we could propose to the customer. So first of all, if the customer wanted to keep the same functionality, the blowing force at the high level, 127 Newton, as it was purchased from the supplier of air knives, and the required pressure, the compressor would be 6.2 bar. In this case, he would need to replace all the tubes and all the connections, everything that comes from the compressor room till the machine. However, it would increase the energy cost, and this is quite logical. To change the system, plus in this case, the pressure would be higher required. So another option would be reduce the blowing force by 22%. So in this case, would get 100 newtons, and the pressure level would be lower. And in this case, the cost would be around 6.4. So basically the situation that we have now. Here, a small remark. It is important always to remember how exactly you use your compressed air, because in terms of the cleaning or in terms of the blowing application, there are two ways to use it. For the cleaning, in this case, the high flow but low pressure is required, in this case for the large surfaces cleaning. And another application, one of the other application, is precise cleaning. In this case, the high pressure is required and low flow. So you see here the difference. And sometimes for the large surfaces, you don't need the high blowing force, rather you need the high flow for this to cover. And those two physical parameters in compressed air, such as pressure or flow, they can just balance, and you can find the perfect balance here. Because the third option, the customer could go and check again with their process team, and we asked, would blowing force to 70 Newton be enough? And the flow here would be 360 cubic meter, but in this case, you need to replace all the tubes anyway, so you need to adjust the system, so you will not have the customer wouldn't have the fluctuation of the flow and fluctuation of the pressure, because this was the main concern, not the quality, because quality sometimes was yes or no, but the problem was the pressure fluctuation. And the energy cost in this case would be about 4.8 dirham. So this will be already lower in comparison. So it would be like 25% savings. However, there is always another solution. So here you see that there is quite long distribution line with small pipes that are leading to the nozzles. So it's a complex and long compressed air system. If if the process engineer agreed that there is an airflow higher required, but the pressure can be reduced, it is always possible to use the blower. So the blower can be installed directly to the machine. It can provide with the high airflow. However, it's not suitable for the very precise cleaning. So in this case, the nozzles, the first solution would be possible. So as you can see, there are 4 options. Here, this short overview, and it always can be find the best balance between the functionality and the compressed air system. However, it is important to start optimizing not the compressed air system, but to optimize how it is used. So first, check the application, how it is used. Are you sure that you need this blowing force? Are you sure that you need this pressure level at the end? Or in case of cylinders, of actuators, you need this application. And then go step by step, using calculations, using models, measurement data, already adjust and adapt your compressed air system to the application, and not the application to the compressed air system. So thank you so much for your time and for your attention. In the next use cases, we will see bigger distribution system, as well as the optimization of the machines that are using the cylinders. And don't forget that you can download the Direktin easycas software in our website, and this is free of charge.